A very good morning to our respected coordinator, Professor Dr. Sumit Banerjee, co-coordinator Dr. Shivendu Mahata, and all committee members, and also our eminent speaker, esteemed faculty members, and all other present over here. Today we have reached to the last day of AICTE ATAL-FDP program. I, Dr. Sneha Sultana, on behalf of Dr. BCREC Engineering College, Electrical Engineering Department, welcome to you all to the AICTE ATAL-FDP program on Sustainability and Innovation in Energy Engineering and Sensor Technology. Today as eminent speaker, we have Dr. Banibrata Mukherjee, Assistant Professor, ATDC, IIT Kharagpur. May I have the honor to read his biodata? Dr. Banibrata Mukherjee received BE degree from Durgapur University in 2009 and the M.Tech and PhD degrees from IIT Kharagpur in 2011 and 2016 respectively. He is currently an Assistant Professor with the Department of Advanced Technology Development Center, IIT Kharagpur. He was previously with the Department of Electronics and Communication Engineering, National Institute of Technology, Rourkela. His research interest includes energy harvesting, piezoelectric and triboelectric system, sensor and interfacing circuit, sensor fusion and its application, MEMS and microsystems, and biomedical instrumentation. Dr. Mukherjee has published numerous research papers in reputed peer-reviewed journal and international conference. Dr. Mukherjee has carried out several consultancy projects, including those from Indian Space Research Organization. He has received the Best Paper Award in IEEE TechSim. Dr. Mukherjee is the recipient of Early Career Research Award. He is also a senior member of the IEEE. Thank you, sir. Please, over to you.
Good morning, all of you. Good morning. Yeah. So thank you, Dr. for your nice introduction, and I am thankful to the coordinator as well as the co-coordinator for inviting me. So let us start our today's session. So today I will discuss about the energy harvesting technology and its interfacing power management circuits for specifically the cell powered system applications. So basically this, this energy is nowadays very important sector, and a lot of researches are going on in the directions of energy technology, energy harvesting, as well as the in general overall energy sector, right? So basically, and of course that is quite aligned to the topic of this particular program as well. So as you can see, this energy harvesting technology, what do we mean by that? So obviously harvesting, it is not like that harvesting of some crop or some cultivation. So here, what do we mean by this energy harvesting? So basically, you know that harvesting of energy, it is nothing but that basically extractions of energy. So we have, suppose in ambient, some another kind of energy sources are there. Like for example, so we have vibrations, we have solar, we have wind. So those are kind of non-conventional energy sources. But energy harvesting means what we want? We want to that extract those other kind of energy and convert them into electrical energy, so that using that energy I will be able to meet the power requirement of some of the electronic gadgets or devices, so that I can make some kind of self-powered system which will not depend on the conventional battery to meet its power requirement, right? So that's why today we will basically discuss on different kind of energy harvesting technology. What are the different ambient energy sources are there? Like those are basically the renewable energy sources, right? And how to convert them, what are the different transduction mechanisms are there through which we will be able to convert those non-conventional energy into electrical energy, what are the different circuits are there, what are the different challenges are there, and how to develop the complete cell-powered system. So those are that prime focus of our today's talk, right? So considering the mixed audiences, so most of you are faculty members of different institute, and some students are there as well, and you may have some mixed background. So the way in which I have basically planned to deliver the talk is that I have basically broadly divided into two sections. So in the first sections I will start with the background of energy harvesting technology, so that even if you are not aware of this particular area, so it will be a good prerequisite for you, where we will discuss the basic concepts. So we will basically build the basic concepts related to the energy harvesting technology, which is quite prominent and dominating area of research. And for that we will learn about various kind of energy harvesting techniques, what are their benefits and applications. Specifically we will focus on the vibration energy harvesting, which is ubiquitously available. So then we will talk about different various construction mechanisms as well as the interfacing circuits, and through which we will build the concepts or basic background to understand the subsequent research activities which we are carrying forward for last couple of years. So after this creating this background, then I will focus on our some previous as well as ongoing research activities in these directions, and there we will talk about our developed energy harvesting systems or the circuits, then also the different kind of hybrid energy harvesting mechanisms, as well as the cell-powered applications in the final. So that I request all of you that at any point of time, if you have any doubts or if you need any clarifications, so please feel free to clear your doubts. Okay. So let us proceed further. Yeah. So yeah, nowadays we cannot think of our today's life without the personal gadgets or different kind of electronic devices and embedded systems, right? So like we can also, apart from that, we have that wireless sensor nodes or sensor networks, we have different kind of medical equipments. So all of them have become our parts and parcels of the life, right? Now all these devices essentially, in order to make them work, we need some battery to meet their power requirement, right? But if we use those conventional battery, definitely we cannot completely replace the battery in every application. So depending on specific applications, if we only rely or only depend on the conventional battery, then that may not be that much feasible or always plausible solution. Why I am saying this? Because if we look into that basically limitations of our conventional battery, then what we can consider, the battery is of course having limited lifetime, right? So that means depending on that rating of the battery, this much ampere hour, it will last for this much time, depending on what load you are connecting with that, right? Then replacement and regular interval. So of course that as it is having limited lifetime, at regular interval we need to replace it. Then when the battery lifetime is gone, so then we need to dispose it, and you know that battery is composed of different chemical compounds, and when we will be disposing it in the environment, it will lead to the pollutions. In some applications, it is sometimes impractical to replace those battery in regular interval. Like for example, if you talk about the implantable medical devices like pacemaker, so that is inside that body, it is there, and of course that battery is having some lifetime for 5 years, 10 years like this. And in regular interval, it may not be feasible to open that heart and in that region and replace the battery. In some other applications, like if we talk about some wireless sensor nodes, like some tunnels are there through which the trains or vehicles can move, and suppose that tunnels can be of 100 meter, 200 meter away long, depending on the tunnels or the road conditions. So there, in order to monitor the conditions of the tunnel, we need to install different sensor nodes which will continuously measure the different parameters of the tunnel, and it will wirelessly send you those signals, so that from the control room itself you can understand what kind of condition is there. So in those applications area also, it is not practical or not feasible, that is sometimes impractical or infeasible to replace those battery in regular interval. So what will be the plausible solutions? The alternative better solutions what we can think of is nothing but your energy harvesting techniques. As I said, what do we mean by this? It is nothing but the conversion of ambient energy which are present in our environment, like this wind energy, wave energy, ocean wave, wind, vibrations, solar, and so on, right? So conversion of ambient energy which is present in the environment into electrical energy, then what we will do? We will process that energy through the power management circuit, and then we will store that processed energy, and within that we will be using that energy, we will be powering up our devices or electronic gadgets or the systems, right? So what are the non-conventional renewable energy sources are present? Like it can include the solar, it can include the vibrations, wind energy, heat energy, radio frequency wave, and so on. So what can be the major applications of this technology? So if suppose, for example, we will be showing some example as well. So suppose somewhere some vibrations I want to measure, and for that I have mounted some sensor over there. Now that sensors will be measuring your vibration or some other associated conditions or parameters. But what I can do there, instead of using the conventional battery, there I can install some energy harvester which will harvest the energy from the ambient like vibrations or solar, and that will be storing it or processing it through its power management circuits, and then that energy will be using to power up your sensors. So like that is the concept, so that you do not need to depend on the conventional uses of the batteries, right? So the major applications can include like wireless sensor networks. We can think of the medical equipment like pacemaker, powering remote infrastructures. Followed by that, we can consider some self-charging consumer electronics, like for example, we nowadays heavily depend on our smart watch or smart gadgets which we basically wear in our body, and suppose when you will be walking, jogging, or different activity you will be doing, so those activity we want to monitor through those sensors. And we can think of some options that suppose when you are jogging or vibrating, so then vibrations will be created, and that vibrations we will be using it to process through my energy harvester, and that energy harvester can be used to power up those smartwatch or those smart gadgets, right? So that is the kind of application, that self-charging consumer electronics concepts. Followed by that, we can think of the smart city, where suppose that is old technology, that on the rooftop we have the solar cells are there. In addition to that, we can think of the other kind of energy harvesters as well, through which you will be trying to meet the power requirement of your household appliances and so on, right? So then of course the next one is the structural health monitoring, like the examples we told for the bridge or the tunnel. We will show that through the example as well, right? So these are the some major application areas. So here I have put some books references which focuses on the different kind of energy harvesting technology and for the autonomous system, right? So I hope the basic background, the requirement, motivations for doing research on the energy harvesting technology along with its application is clear to all of you. If you have any doubts, please let me know.
Sir, the battery power you were saying is that how long it can be stored in the system?
Yeah, so how long means, so of course that depends on suppose what kind of energy harvesting technology we are using. Based on that, how much power we are generating, then that power, of course, suppose the raw sensor output or the raw transducer output, it may not be directly compatible to that your sensor input requirement. So then we need some in between interfacing circuit blocks which will be basically processing that energy and make it compatible so that you can use for powering up your devices. Now here also finally you need to store it, and for storage purpose normally we can think of some supercapacitor which is having that higher energy density, or you can think of some rechargeable battery which will be that charging through the energy harvesting system, that you can store it, and then it depends on how much energy you are able to extract. Based on that, what is the power requirement of your sensor, based on that it will tell you that how much time you can drive, right? The same kind of thing. Suppose if it suppose 100 millijoule for example if I get, so then that is the total energy which we are getting, and then of course you need to know that what is the power consumption of your load, and as per that you can understand how much time it can basically run the device.
Any fixed formula is there, sir, to calculate that this is the thing, or I can have some?
No, that depends on the energy harvesting technology, that how much energy or power you can generate. And suppose 100, that normally the battery capacity is written as suppose 1 ampere hour. So that means if some load draws 1 ampere current, then it will sustain for 1 hour.
Oh, 1 hour.
Now that's for example. So similarly, if I have suppose 100 milliampere hour, so then it depends on that. If suppose one device or basically one load consumes 2 milliampere current, so then 2 milliampere, that means 50 hour it can drive. So that depends on what is the stored energy and how much is the current requirement or the load that requirement. So that if you divide, you will get that the time duration. Right? Any other question?
Thank you.
If not, let us proceed further with the example of these wireless sensor nodes for structural health monitoring application. So suppose if we consider, suppose here some bridge is there or railway tracks or some tunnel, you consider this. And here as I said, there are a lot of sensor nodes are installed over here. Why we have installed this? So that these sensors will measure basically different parameters, structural parameters. For example, the stress or that displacement, or from there basically it will estimate that how the bridge life is there, if there is any crack or not. So those kind of things can be detected by these sensor nodes which will be installed in this bridge or tunnel or this so that you can consider some structure. And now these sensor nodes will be monitoring those different parameters like stress, strain or displacement, force, that even you can think of the resonant frequency, the crack. So accordingly those informations normally wirelessly we send it to the base stations. From that it is uploaded in some server and it is stored in some database, and the operator can monitor or track the server to understand that what is the conditions of the bridge. So basically by analyzing those sensory data. Okay. So now in these applications, as I said, that if I consider some tunnel, so then it is that impractical that you will go at every 5 days interval or 7 days interval to replace those battery. So that's why what we can think of here, these some energy harvesters units we can put in the vicinity of the sensor nodes, and those energy harvesters will be extracting the energy from the vibration as well as the solar or other ambient energy whatever is available, and then that energy it will be using to meet the power requirement of these sensor nodes, so that you do not need to depend on the conventional battery, and in regular interval you do not need to replace it. But of course specifically the energy harvesting technology what we are saying, that mostly for the low power sensing applications or the electronic gadget applications we are talking about, because the electronic devices which we are using in our day-to-day life, they do not consume that much power, So that's why those whose power consumptions you can consider in the range of some milliwatt or microwatt, that kind of range, or in millijoule, microjoule, that kind of range. So there are the good candidates which can be basically powered by this kind of energy wasting technology, but that immediately you may not think of that using that energy you will be able to run some your normal AC or that kind of high power basics, right? So but since that majority of our sensor nodes, as far as the sensor nodes are considered, or majority of the applications with respect to the electronic gadgets are considered, they consume low power. So that's why for them the energy harvesting is very good candidate to meet their power requirement. So in this context, as you already said, that multiple sensors are installed here to monitor the conditions, and these sensors can be powered by the ambient vibration energy harvester. So the vibration energy harvesters or the solar energy harvester or whatever what we will be putting over here, what can be the typical components of the unit? The first of all, it will include the energy harvesting structure. So that is kind of the transducer which is converting those ambient energy into electrical energy. So that is the first primary block required. The second block requirement is the energy or power management circuit, which will basically convert this raw energy output into the compatible energy output, or basically to increase the overall efficiency. We need to interface the power management circuit so that the required level of energy which we are getting as the raw output, that we can amplify significantly, and the overall efficiency we can improve it. Further, we need to store it through some supercapacitor or rechargeable battery, and finally that stored energy can be used to meet up the power requirement of microcontroller, sensor or other peripherals as well, right? So this is that background examples and the basic components of the energy harvesting unit. Okay. Now, if we want to list down that what are the dominant energy sources, so of course the first of all we can consider some vibrations, like the examples we told about this structure, like some busy bridge is there, and through that bridge regularly lot of vehicles are passing by, and because of that vehicle movement the vibration is generated. Or suppose some electric machineries are there which are continuously running in labs or some industries, and because of that the vibration energy are produced. And those energies are, if you do not use them, it is completely wastage energy. So some washing machine is moving as per your requirement, so then that energy also, if you do not use them, that is wastage of energy. So our objective is to use those wastage energy and to convert them into electrical energy, so that you can process it further to meet up the power requirement of your electronic gadgets. So like structural machineries, wind, you can consider the wind energy as well, and ocean waves also, this comes under the vibration energy source. Further we have so this you can consider, suppose this is the vibrations and this is one transducer which can convert the vibration into electricity. So you can think of the first transducer which will come into your mind is nothing but the piezoelectric transducers, right? Which when the piezoelectric transducers will be exposed to vibrations, it will give you the output voltage, right? So then we can consider the solar cell. Of course, the solar cell, depending on the thermal energy. So like if I have some, you might be aware about this concept of Seebeck effect, based on which the thermocouple works. So when the junction temperatures are different or there is some temperature gradient, so based on that the electricity will be produced. So that is based on the thermal energy. Then you can consider some radio frequency energy as well. So the radio frequency, we have a lot of electromagnetic waves because of the communications or those waves can be, RF waves can be captured by that antenna receiver, and that can be converted into DC voltage through the RF to DC conversions, and that also you can use it for further processing purpose. So these are some of the sources, and out of those sources, if we talk about the vibration energy sources, so that is widely available source. What are the typical source of vibrations? We can think of like as I told, the machineries, different equipments, car engine, bridge, washing machine, HVAC of the vents in the building, then we have the wind, ocean wave, and so on, right? So these are some of the sources of vibrations, and we will mainly focus on the vibrations, but the other sources also we will give a glimpses on that. So if we talk about the vibration energy sources, typical vibration amplitude which can be obtained from this source which we have mentioned over here, From those sources, typically the vibration amplitude you can think of in the range of, in terms of acceleration, 0.1 meter per second square to 20 meter per second square. Quite low amplitude you can consider, and the frequency is also typically low frequency, less than 200 Hz. These are the available sources basically, right? So of course that nothing you can get at the pre-op cost. So the energy harvesters, it is converting the ambient energy to electrical energy. Free of cost, it will not give you the electrical energy, is not it? So whatever that ambient energy is there, based on that only you will get your required energy. It is not like that some small vibration is there and you cannot expect very large output voltage, right? So that is the energy conservation law must be validated there. So these are the available sources and the typical ideas I have given from this. Now if we talk about the vibration energy harvesting, what are the popular transduction mechanisms? The first of all you can consider the piezoelectric, as I said. So suppose if you consider this is some cantilever beam is there, here this cantilever beam, this is the fixed end and here is the free end, and when it is exposed to some vibrations, here I have deposited or mounted some piezoelectric device over here, and when it will be exposed to vibrations, from the piezoelectric you can get the corresponding electrical output voltage. So that is one transduction mechanism. The next transduction mechanisms for vibrations we can consider as the electromagnetic, that simply works based on the Faraday's law of electromagnetic induction. What it happens here? So if you consider suppose this is one some typical structure is there, cylindrical structure, where at the bottom if you consider some permanent magnet is put over here. And here you can consider some mass spring arrangement is there, here is the spring, here is the mass, and across that mass some coil is wrapped around. Now when this whole system will be subjected to vibration, what will be happening? With respect to this coil and permanent magnet, there will be relative displacement. And because of that, flux cutting will be there, and based on the Faraday's law, the output voltage will be generated across this pickup coil, and of course, as your vibrations will increase, your output voltage will also increase. So this is the electromagnetic concept. The next one, another recent topic is with respect to the triboelectric based technique. What do we mean by this? Triboelectric, it basically depends, or it basically relies on the principle of that contact separations and electrostatic induction. So what do we mean by that? If you look at this diagram, here you can see this blue one is one material and this grey color is another material. So these are the two materials, and this orange color top and bottom side, they correspond to the electrodes. So when this particular kind of structure is subjected to vibration, then what will happen? This blue structure and this ash color material, these are the two different materials having different electron affinities. So one is suppose highly electropositive, another is highly electronegative. In that way I have to choose these materials. Now when the vibrations will be applied and contacts, that continuous contact separations will be there between those two materials, then because of this that charge separations or basically charge transfer between these two materials, and because of this electrostatic induction, the voltage will be produced, and this particular technique is called as the triboelectric mechanism. So these are the three most popular mechanisms as far as the vibration energy harvesting is concerned, right? So we will discuss all of these mechanisms, and of course the other sources also we will talk about, and then we will also see you the research activities which are going on in all three transduction mechanisms in our group. So, yeah. So till now, I hope it is clear to all. Any doubts or questions? Yes.
Electromagnetic, just one minute.
Yeah, electromagnetic. What I said that this here you can see this is the whole cylindrical structure you can consider, and here you have this permanent magnet. Okay, and here you have some mass spring arrangement. Here the spring is there, and here you have this mass, and across that mass some pickup coil is wrapped around. So when this whole structure will be subjected to some vibration, so then what will happen? This mass spring system will be moving, and there will be relative displacement between this permanent magnet and the pickup coil. So because of that relative displacement, you know that here magnet is there and some coil is there. So based on Faraday's law, across this coil the voltage will be produced. Okay.
Sir, if I talk about the suppose washing machine or any motor, is it applicable electromagnet? Because motor moving like this, some vibrations should be there. That is helpful to produce the.
Yeah. So basically, for this you need vibrations. This whole structure is there. That is your harvesting structure what you are designing. So this structure is there. When you will be, so suppose this is the structure you have created and some machine is moving, whether it is washing machine or electric machine, that is moving, you are putting this. So there will be relative inside this, the relative displacement will be there between the coil and the magnet, and because of that, it will give you the output. So if it exposed to some vibrations, it will give you the output.
Moving turbines or something we can think of that keep creating here.
What?
Fast moving machines that can be applied so that that vibration will be created and energy can be produced.
Yeah. So if you increase your amount of vibrations, of course the output voltage will also increase. Right? Yeah. Any other doubts?
Sir, another here we are saying about the hybrid energy, solar and all this is energy produced and the cost of the deployment is more than the energy producer because we need some.
Yeah, that is very good question because we need to think of the economic point of view as well as the trade-off.
Yes.
So suppose the amount of energy, how much we are extracting, to extract that much amount of energy, how much cost or effort I need to give to develop those energy harvesting system. I think that is your question,
Yes,
right?
yes, sir.
So that is definitely a very good point which we need to that keep in mind while designing the structures or carrying out the activities in this direction. So there, yeah. So like if you do not use this, the energy is wasted, and after you mount those devices, then you are getting some energy, but our objective should be while we are designing our this harvesting structure along with the circuit, so that definitely that should have low cost, because we cannot think of very large structures, because for that again you need to give more money and more cost, and the amount of energy which you are getting, that may not be basically that trade-off that you have to keep in mind, and you have to see that what kind of the optimum way in which way you can use it. So if it satisfied your economic point of view or economic purpose, then only of course we have to go there, right? So we will show you some demonstrations of that activities where we are we can develop using low cost devices. Okay. Yeah. Any other doubts? So let us talk about this discussion that construction mechanism one by one. So some of you already might have been exposed to this. Just for brushing up and for continuation purpose, I will talk about this. So suppose if you consider this piezoelectric, as I said that piezoelectric basically shows two kind of properties, right? Direct effect as well as the reverse effect. When these piezoelectric devices will be exposed to vibrations, so then it will produce you the voltage, that is called as the direct effect, and it shows the reverse effect as well. If it is exposed to some AC that EMF signal, so then it will produce you the vibrations, right? So of course for this energy harvesting mechanisms, we will extract the direct effect. When it is exposed to vibrations, it will produce you the voltage, and of course it is material property. So some specific material will give you this piezoelectricity property. So we have two standard configurations. One is called as the unimorph configurations, where you can see suppose this is your cantilever structure or some plate is there, where this end is fixed end and this end is free end. So you can see that this is your structural layer, this red one, and the top one is the piezoelectric layer, green one. Okay. So in this case, the piezoelectric is put on the one side of the structural layer, and in second case, the piezoelectric is deposited in both sides of the piezo layer, and this configuration is called as the unimorph, and this one is called as the bimorph configurations. So these are the two standard configurations, and of course in case of bimorph, you can get the output voltage from both top and bottom sides, and you can get the larger output. In terms of operating mode, it is having two kinds of operating mode. One is called as the D33 mode, another is D31 mode. So what do we mean by this? So D33 mode means, so this 3, 1, 2, 3, this basically you can map it with respect to our X, Y, Z axis kind of thing. So in 3-3 mode, what happened that suppose this is your piezoelectric crystal, if I apply the force from top side, in the same directions I am taking the output voltage. Across this top side, portion and the bottom portions, I will be taking out the voltage output, and the directions of the voltage output taking and directions of applied force are same in D33 mode, whereas in D31 mode, I am applying the force across these directions, and I will take the voltage across the other axis which is perpendicular to the force directions. Right? So these are the two mode of operations, and if you look at the datasheet of the piezoelectric device, there the sensitivity will be written that if I operate it for D3, that 3 mode, then what will be the sensitivity for this much vibrations, how much voltage is there, for 3-1 mode, how much is the sensitivity, in terms of for that delta input, what is the delta out, right? So in this case, delta input means in terms of accelerations or vibrations with tail input and output in terms of voltage. We can think of this PVDF polymer, aluminum nitride, zinc oxide. So these are some of the commonly used materials which exhibits the piezoelectricity property, right? So this is about the piezoelectric transduction mechanism, and what are the features? The features are typically where it is exposed to vibrations, it will give you larger output voltage. The structure is very simple. Simply on some cantilever structure you can put your piezoelectric device, but the piezoelectricity is the material property, so you have to choose the proper material in order to extract the piezoelectricity property, because all material will not show you this property. So whichever will be showing, that you have to choose. And also this here, like I have noted, I have listed 1, 2, 3, 4 main materials. Now all the materials will not give you similar output. So depending on the sensitivity or depending on the material property, some may give more output, some may give less output. So as per your requirement, you have to choose that. Now another thing, like the cost, you have to see that out of this material, this, of course you know that polymers are quite low cost buy. So that's why out of this PVDF you can choose, because that is typically low cost material and which exhibits the this piezoelectricity property. So some material which is very high cost but sensitivity is very high, so that you have to see that whether we should go for that or not, because you have to think of the economic point of view actually. So this is about the piezoelectric mechanism. So next one, let us discuss about this triboelectric mechanism. So what do we mean by this, as I explained in brief. So suppose in triboelectric it relies on the coupled effect of contact electrification and electrostatic induction. So what do we mean by this? In this case, I need to take two different materials. One should be chosen as the electropositive, another should be chosen as the electronegative, so that when they will come in contact, the charge transfers will be there. And then again, if you separate it out, again charge redistributions will be there, and across the electrode I can get the output voltage, right? So here through this image you can see, suppose this is the first condition. As before that, the piezoelectric what we discussed, as I said, that nothing I can get at the free of cost. Suppose I have my piezoelectric crystal and just on the piezoelectric crystal is there and some 10 kg weight I am putting on that. So I may think that 10 kg some load I have put, so because of that some force is being experienced, so accordingly it will give you some voltage, right? So what do you think that on the piezoelectric, if I put some 10 kg weight, what kind of output I can get? I am giving some hints option. Option 1, 0. Option 2, some constant voltage. Option 3, some impulse voltage. Option 4, none of the above. So what can be the options for this? Very good. So because piezoelectricity, that so if you put this at that time, it will give some impulse, then it will be 0. Because if you give some continuous vibration, then only you can get the output voltage, right? So nothing you can get free of the cost. If you give some continuous vibration, then only that will be converted into electricity and it will give you the corresponding output, right? So now coming back to this discussion. So suppose here you can see this blue one is one tribomaterial, this lower one is another tribomaterial grey color, and suppose if I consider this top one is that electropositive and bottom one is electronegative. So then what will happen? So suppose initially they are not contacted, so some gap is there, and top side this orange and bottom side orange, they correspond to the electrode. And of course here in the figure, don't think that they are sorted. They are not sorted actually. Although in the figure it looks like they are sorted, but of course they are not sorted. They are separated. So when some initial gap is there, then no vibration, nothing is there. So then across these electrodes I am connecting some meter. So of course it will give you the 0 reading. Now when I press it, and at the time of the pressing, what will happen? These two plates will be contacting to each other, and here plus, here minus, those charge redistributions will be there. But still, I will not be getting any output. When I will get the output, I touch it, and then again when I am separating it out, at that point of time you can see the charge, that this charge is transferring from the tribo material to the electrode, and because of that the EMF is produced. Right? Then again, if it is kept at that positions for some amount of time, then again you will be getting the zero output, because continuously if you don't apply vibrations, it will not give you the output voltage. Then again if you connect the touch them, then again you can see the output voltage is there. So continuous contact separation if you do, then only it will give you the continuous output voltage. And the most important advantage of this triboelectric is that the material which we need to use it, they are very low cost and available in our day-to-day life household applications, like simple paper, wood, our clothes, right? So those kind of materials, even the Teflon tape, so those kind of materials can be used as the tribo materials, normal aluminium foil, right? So, but you have to keep in mind, one material should be electropositive, another material should be electronegative, then only you will get the maximum benefit out of this. Okay? So, here that the explanations what I have given, that is written over here. When two dissimilar materials are brought into contact with each other, electrostatic charges are generated on the surface of the two materials depending on their different electron affinities. When those two materials will be subsequently separated, a voltage is developed which forces the electrons to flow between the two electrodes attached to those materials, developing an alternating current. So what I explained, that is written over there. What are the triboelectric series material? As I said, very low cost household materials like paper, your Teflon tape, silk, wool, nylon, PVDF, PDMS, these are the kind of some polymer, and aluminium foil. So those, even wool, so those you can think of as the triboelectric material, right? So this is about the triboelectricity property. It is having important feature. It can produce you the high output voltage. The structure is very simple, and the tribo materials which we use, they are basically very low cost and they are available in our household. Right? So this is about the triboelectric mechanism. Yes.
What is the range of the voltage and current? What is the range of power in this?
Right. So typically for this piezoelectric and triboelectric, these two mechanisms which we discussed, there the voltage level can be very high. Even you can think of 20 volt, 50 volt, even for tribo you can get the 100 volt as well. But the current is relatively low. The current you can expect hardly in some microampere range. So the overall power, it can be within microwatt to milliwatt in that range. So ultimately, if you want to use it for powering some sensors or some loads, which will matter, the ultimate power will matter. Only voltage high will not suffice the purpose. So the current requirement also should be met. So that's why we need to think of all those things, and we need to see from the ambient how much energy we are able to extract, so that I will be able to choose that only it can send the power of these nodes, this many number of sensors. Accordingly, arrays of harvesters you can connect in series or parallel depending on their configurations, so that you can basically increase the overall output or in terms of voltage, current as well as the power. Right? Yeah.
Sir, there is a metal, in principle, you can written over here two dissimilar material. So how can this would be, say, the paper, silk, wool, would be as a metal?
No, I did not say metal. These are, see, this blue one and this grey color, these are the actual tribo materials. And these tribo materials are this one, paper, Teflon, silk, those are. But to get the output voltage, you need some electrode, metal electrode. So this orange color, they correspond to the electrode, that is just to take out the connection. So, but actual tribo materials are not metal, they are this kind of normal household materials. Okay?
It was like the brass in the motor, then the brass will be connected with this one. It will be connected.
No. That
Upper and lower.
this structure is, suppose you have this kind of structure is there. Now that structure assembly, you will be vibrating on the vibrating platform, you will mount that or install that. Now when vibration is there, accordingly inside your structure, your device is moving, that structure should, that material should be moving. So this whole things you will be building, and after that you will be putting it on the vibrating platform. So in that way.
No, collecting part.
Yeah, so collecting part, this electrodes, so that so this material is there, on top of that the electrode needs to be attached. And from that you can solder that some wires, and through that you can take out the connections to get the voltage. Okay.
And sir, here in this case, is the power output is means directly proportional to the surface area of the contact point, or?
Yes, so of course the surface area is very important. As your surface area will increase, your overall power will also increase. And for each of these there are actual different mathematical equations, and all those equations are there. And essentially this piezo and tribo, if you look at the electrical equivalent circuit, it will come as some constant current source, not constant depending on the vibration, some current source in parallel resistor and capacitor. So that is the kind of electric equivalent circuit for this, right? And now this, so based on that electric equivalent circuits, you can. So what was your exact question was there?
Sir, it is the power output is directly
Yes,
proportional to the
yes.
surface.
So now that internally it will be having one capacitance as well as the resistance, and of course you can think of that capacitance means, of course, that will also depend on the cross section, that overall overlap area, like we know normal parallel plate C equals to epsilon A by D. So based on that will give you larger capacitance as well, and the overall power will also increase. And mostly you can consider that relationship is proportional. As your area will increase, your power will also increase. But for each of them there are detailed derivations are there, how the current or voltage generation is related to the force or vibrations. So those detailed expressions are available as well. Any other doubts or clarifications? If not, let us proceed further. So next, here you have, this is the permanent magnet, this is the mass spring system, and the coil is wrapped around the mass. Applied vibrations will cause relative motion of the conductor mass in the magnetic field provided by the permanent magnet, as already we explained. And this is based on the Faraday's law of electromagnetic inductions. So accordingly, through this pickup coil, the EMF voltage will be produced. Right? So that is about the electromagnetic transductions. In this case, the important thing is that here typically the voltage amplitude is typically low, but the current amplitude is typically high with respect to the previous two mechanisms. In piezo and tribo, your voltage level is high, but current level is relatively low. In this case, your current level is relatively high. High means, of course, it is not in some very that large ampere, but amount of, if in that case it is in microampere, so here it will be hundreds of milliampere or like this. And typically the voltage is relatively low. So what we can do, if we can basically combine these techniques together, so then you can basically essentially increase the overall voltage as well as the current, which will lead to the overall power improvement. Right? So that can be also another important opportunities. So the important features are high output current. The design is relatively complex with respect to the piezo and tribo, and here we need the specific magnetic materials. Right? So these are about the electromagnetic transduction mechanisms. So with this we have understood the concept of the vibration energy harvesting techniques, and for harvesting the vibration energy and converting them into electrical energy, we have discussed mainly about this piezo, tribo and electromagnetic, these three concepts. Right? So till these portions, if you have any doubts, please let me know. If not, let us move forward. So what are the other sources? We have the photovoltaic source. Of course, the solar energy is the source in this case, significant source of power harvester. However, this power, basically energy source is periodic, and it is intermittent, and it is affected by the light intensity. So in the daytime only you will get the solar light, and even if the cloudy or rainy weather is there, you will not get the solar light. So that's why it is periodic and intermittent, and of course the output will depend on the intensity and availability of the solar light. Right? And in this case, of course, photovoltaic cell is a preferable choice, which typically consists of the PN junction, and on the PN junction, when the solar light, basically photons, gets incident on this solar cell, so then it basically induces the electron hole pair. Here you can see that, and that is the property of the solar cell, the specific solar cells. When it will be exposed to the proton, the electrons flow will be the electron hole pair will be generated, which will in turn produces the current when I will connect some load across this. Right? So in this way it is converting the solar energy into electrical energy.
Sir, in case of PV cell, if the solar plate is this size, so how much it can develop the power? Is
So
it for the 1 centimeter or 1 square centimeter?
Yeah, yes. So you know that if you procure the solar cells, so the rating will be there. So depending on the size, so depending on the, suppose if you consider some this maybe some half of this if you consider, so that also depend on what material is used to manufacture that, and typically that 3 watt, 9 watt, so that kind of wattage can be also basically the rating will be given by that, and the amount of that you can expect the, so that depends on the, of course, the dimensions of the solar cell, and based on that the rating as well as the, you know, this open circuit voltage, how much it can give in the full intensity of the light. And also if I use suppose some MPPT kind of circuits, then what will be the maximum power point voltage. So those specifications can be given or can be achieved from the specific data sheet.
Sir, there is any formula that we can calculate the, from the intensity of the light, we can calculate the this size of solar panel. Okay, this much power it can generate.
So,
sir, this type of question may arise that 1 square centimeter solar plate, how much power generate? I have seen the.
So we can do that.
Yeah, you can do that if you, but for that you need to know that because different materials can have different this sensitivity. So if you know the either sensitivity or the what kind of materials is being used, so then definitely you can calculate that estimate that this can be there. But the same thing you can, if you ready-madely procure, so then in the manufacturing data sheet already it will be written the things. If you don't know that, you can, if you the required informations are given, definitely you can calculate theoretically also.
Formula is there, sir, to calculate. Formula is there.
There
If
is
this is
a
the
simple formula. You get 1000 watt per meter square. Okay, 1000 watt per meter square power. Okay.
So the dimensions.
And you have a specific specific efficiency of your solar panel. Okay, it is 20, 22, 23%.
Okay, so 1000 watt per meter.
1000 watt per meter square. It is standard test condition.
Oh, either 1 meter this size or 1 meter this size, it will
Yes,
generate
yes,
1
1 square meter. 1000 watt per meter square.
But
And
it
you have
depends
a
upon
efficiency
the-
of 21, 22, 23%.
If it is the 2000 meter square, then automatically
Double.
proportional.
So in this way you can calculate.
Again, it depends
Right.
upon the electron, how they are getting charged in the cell also. No? So because every cell may not get equal amount of sunlight.
So that will come under efficiency.
Yeah, that is the average kind of things. So yeah, so that is about the solar cells. So next, let us move forward to the other kind of sources. Like the next one is the thermoelectric. So as I said, that is based on the thermal energy. Here we are converting the thermal energy into electrical energy. So if I consider some metal, and if that two sides of the metal are applied to different temperature, or if I consider two different metals, dissimilar metals joined together and two junctions are applied different temperature, so then because of the temperature gradient, the electrons will be excited, it will be growing, and because of that also the voltage will be generated. So that is kind of the Seebeck effect, and based on that, what we can do, we can convert the thermal energy into electrical energy. Okay. So next what we can, so here direct conversions of temperature difference, we can get the temperature difference, we can convert it into the corresponding electrical potential. So this is primarily because of the charge carrier diffusions, and this is about the thermoelectric. So here we are able to convert the thermal energy into electrical energy. And another source which we are talking about is the radio frequency energy. So if we basically receive this electromagnetic wave through the receiver, so then we have the RF to DC converter circuits we can use, and through the power conditioning block also we can get the required electrical output, and in this way we can convert the radio frequency energy into electrical energy as well, and that is also another kind of techniques through which we can convert the ambient energy into electrical energy. So these are some of the important sources we have discussed, like typically the vibrations, solar, then we have the thermal as well as the radio frequency, and also we have discussed about the corresponding associated construction mechanisms, right? So with this, let us take the break, and then we will move forward to specifically the vibration energy harvesting techniques along with their interfacing circuits, and after that we will discuss about the ongoing research activities. So let us understand little more details with respect to vibration energy harvester, and also let us see some interesting applications. So these applications these are taken from some research papers to give you some idea about this research trends. So application will include the health monitoring, wearable electronics, cell phone devices. So suppose if we consider this person is walking or jogging, as I said in the beginning, so like suppose we want to monitor the body activity during the jogging or walking, and for that we have installed some sensors in our body. So then what we can do in the shoe sole, so under that shoe sole we can put those piezoelectric kind of energy harvester mechanisms or devices along with its circuits. When we will be stepping or jumping, so then depending on that energy will be produced, and those energy will be used to power up those sensors which we are wearing through our bodies to give those readings of different activities. Similarly, if we consider suppose some sweat sensor, those kind of some body sensor are installed, so then also what we can do, some energy harvester along with circuits can be basically installed on the body, and those due to the vibrations or the body activity monitoring, or that this the kind of even from the electrochemical mechanisms also some sensing or some harvesting mechanisms are there, which basically converts the bio energy into the corresponding electrical energy, biofuel, based on the our sweat. Different ions are there, based on their exchanging, so different those can be also converted, the chemical energy into electrical energy through the energy harvesters, and that can be used to power up the sensor nodes for wearable electronics applications. Another interesting applications you can see for this smart mask application, that is very recent application, and this one basically invented just during the pandemic things. So you know that when in the masks, that have been very popular for last couple of years due to corona. So there the concept is such that the triboelectric mechanisms which we discussed, so that triboelectric mechanisms is included in the smart mask. So the mask is considered some kind of smart mask mechanism, where this is the kind of the overall mask you can see, where inside the mask itself one triboelectric layer are there. You can see TL1, TL2, these are the two triboelectric materials you can consider. This is positive, this is negative, and here we have some electrocution layer. So what happens basically, so suppose when you are wearing this smart mask, this is also definitely the conceptual level, and some preliminary that basically the that validations have been done, but not in commercial phase, but that has scope for carrying out the research activities. So suppose some virus, or suppose coronavirus or other kind of virus aerosols, when we try to go through the mask, then what happened during our basically the respiration? During the respirations, what will happen, or during respirations or mouth movement or chewing, so those kind of activities, what will happen, the triboelectric layers may get in contact separations, and because of that the electricity, that high electric field can be produced, because the voltage level is high, although the current level is relatively low, and then using that voltage, we have basically, here we have some metal kind of structure, metallic mesh kind of structure is there, and those metallic mesh kind of structure are basically some voltage or basically charge is being applied to this particular layer, and when the virus will try to penetrate through this layer, then they will be basically electrically shocked, and based on that those viruses will get killed. So that is the concept of smart mask, and here we can see one beautiful application of the triboelectric layer, right? So in these directions, so some theoretical developments or analysis we have done, and some practical implications we are trying to do. So with respect to the smart house, as you can see on the smart house on the rooftop, we have that we can think of the hybrid mechanisms like solar cells are there, some vibration harvesters are there, which is basically converting the wind energy into electrical energy, and all of them are hybridized together, and based on that it can be useful to meet up some power requirement of some that low power household appliances, right? So these are some important application domain to give you some idea or that some interests in this particular field, and you can see these are the real applications area. Then another applications we are focusing on suppose some tire pressure monitoring system. So you know here we have the tire is there, on the rim we have some pressure sensor is there. So that pressure sensors will be basically continuously monitoring, measuring the power, and suppose through some wireless medium it will send the pressure information to the driver. So here what we can do, instead of using conventional battery, we can put some energy harvester unit, because when the vehicles will be moving, so that vibrations will be created, that vibrations will be converted into electrical energy, that energy can be used to meet up the power requirement of the tire pressure sensors. So inside these tire pressure sensors, so here you can see you have the main sensor like pressure sensors, accelerometer sensors, here some signal conditioning circuits, transmitter receiver, then different signal conditioning modules are there. In addition to that, here we have this energy harvester module, energy scavenger, energy storage, power management module, and these power management modules are also there. This is nothing but your energy harvester, which is converting the vibration energy into electrical energy, and that is meeting the power requirement of your those pressure sensor. So this is just to give you the idea, some interesting ideas and applications of this vibration energy harvesting technology. And of course, we should not expect to meet the power requirement of very large power devices, but at least for low power applications, low power sensing node applications, even if for that applications we can use the energy harvester, that is more than enough in our intended application area, right? So now gradually, so these are just I have created some basic background and platforms with respect to this particular area. Those who might have some background, it is quick brush up for them. Who might not have any background, I hope you have got some good amount of idea and overview of this particular area. And now we are gradually moving forward to the research orientations. And since some of you are faculty members of different institute, so I hope the way in which I have planned that in this particular area, how we have started the work from the scratch, and gradually what is our current status, so some kind of that chronological flow I will discuss, so that for the new researchers it may be helpful for you to either to create, that have some kind of benchmark or some reference. Of course you can do even with respect to better than this, but there is some reference or benchmarking, some idea you will get, right? So now let us look at that. Okay, so we have built some basic concepts with respect to this energy harvesting technology, and specifically the vibrations concepts we are focusing. Now let us see what are the performance improvement aspect of the vibration energy harvester, right? We have got the basic concept. Now how to improve its performance so that the overall power can be improved and it can be used to drive multiple sensor nodes or multiple loads together. So with that things keeping in mind, the salient features for performance improvement, one is the suitable materials, because you know that in this case, while developing the harvesting units or the transducers, the material is very important because different materials will be having different sensitivity. So first requirement is the suitable materials. Second one is the design, that the structure which you will be designing, the cantilever, that one simple example I have shown. Apart from cantilever, there can be other kind of modified that structural design as well, which can give you better performance. So that is the next aspect, is the design. Third one is the frequency tuning and increasing bandwidth. That is also another very interesting concept, because you know that suppose I have the piezoelectric transducer is there. What I said, when it is exposed to vibrations, it will give you the electric output. Now the vibration, suppose if and this piezoelectric, you can think of kind of mass spring damper system, the equivalent model of that, mechanical model. And the structure which is vibrating, that can move in different vibrations. Like I said, that typically the vibration range is up to 200 Hz maximum. If you walk, it can give you hardly 1 Hz, 5 Hz, that kind of Hz. If you are walking, so then if you are running or jogging, so then frequency will be more. Or some bridge is there, if the vehicle is very frequently passing, then frequency will be more. If less frequently, then frequency will be less. Likewise, different kind of frequencies are there. Typically it is within 100 Hz. Now suppose if my structure is moving at 100 Hz and the structure which I have put over here, if I consider that mechanical model, that is also kind of mass spin damper system, and that is also having some internal resonant frequency. So in our school days we learned that when in the bridge basically that lot of soldiers are moving, so if there is some rhythm, particular rhythm is there for a specific rhythm, it can damage the structure. What is that? When resonance will be there, right? The resonant frequency of the structure, if it matches with the stepping of those soldiers, so then your maximum vibrations will be there, is not it? Similarly, the piezoelectric device which we will be developing, if my ambient is 100 Hz, then how should I choose the frequency of this structure so that it will give me the maximum output? That also should be 100 Hz, the resonant frequency, is not it? Accordingly, I have to choose what should be my stiffness value, mass value, root k by m, that is the resonant natural frequency, right? Now, it is not like that you have developed one piezoelectric energy harvester with 100 Hz. Now, it is not like that the ambient is fixed. Sometimes it can 100 Hz, sometimes it can 20 Hz, 200 Hz, like this. So then, in order to get the optimum performance, obviously it is not better that for 100 Hz you will be developing one harvester, for 200 Hz another harvester. That is not a good choice. Instead of that, if in the one harvester itself, if I have a larger bandwidth, I can use it for multiple applications having multiple frequencies. Is not it? So that is the important aspects with respect to the frequency tuning and increasing bandwidth. And the final one is the new design of power management circuit. Right? So if depending on the circuit also, which can be interfaced with these harvesting units to increase the overall power. So just the material design we understood, the frequency tuning let us illustrate a little more, and then we will deeply focus on the power management circuit aspect as well. So frequency tuning, as we said, that to obtain maximum output, the harvester resonant frequency should match with the source frequency, and harvester structure should achieve a sufficient operational frequency range so that the same structure can be useful for multiple sources. Tuning mechanisms should obtain a suitable degree of frequency resolution. So if some kind of tuning mechanisms are there through which I can adjust the bandwidth or improve the bandwidth, that will be favorable for me. So in that context, just a very simple example. So suppose if you consider that one cantilever is there. So one cantilever, if I consider some particular length, weight, thickness, then it has standard formula to calculate what is the resonant frequency or the natural frequency, right? So of course, if I have one cantilever, I have only one resonant frequency I will be getting. If I want to use it for, and one resonant frequency means, suppose if I consider this for one cantilever, this can be the resonant frequency response. The second one, this can be the frequency response. Likewise, for multiple cantilever, this can be the multiple frequency response are there. Now, very simplest thing will be if you choose some array of cantilevers with different dimensions, and if the dimensions are very close, suppose one is this much, another is this much, another is this much, this much. Likewise, if you have some sequence of array of cantilevers, and if their resonant frequency are very closer to each other, then what I can do, if suppose n number of cantilevers are there with these peaks are very closer to each other, then what I can consider, these all I can consider almost equivalent to a straight line, so that the overall bandwidth can be like this. So this red one corresponds to the individual cantilever's frequency response, and this blue one corresponds to, if I have all of them together, so then we can consider this is the overall bandwidth or the frequency response of the particular structure. So you can consider, suppose here array of cantilevers are there having different dimensions. Although this is not up to the scale, so these cantilevers are having different dimensions to have different resonant frequency. So that is one simplest design I am saying.
So it is of 3 array.
No, this is just for example 3 figures are shown, but here you can have a number of this kind of cantilevers are there. Having
Sizes
different
are
dimensions.
varying, sir. Sizes are same.
No,
Sizes
different. So here in the scale it seems similar, but actually there are different dimensions are there. The dimensions have to be different so that their resonant frequency will be also different. But
cantilever has upper layer color and lower layer color is different. What it means?
no, it is made that on the cantilever some piezoelectric is deposited. So suppose lower one you can see 1, 2, 3 layers typically you can consider see here. So the lower one is the actual structural layer. Like structure can be some aluminium or some kind of material.
Lower.
Lower one. Then middle one you can consider as the piezoelectric material, and the top one you can consider as the electrode. So basically from which you are taking the output voltage.
So this 3-1 has a different nearby resonance frequency. Different,
Yeah,
but
so-
nearby.
Yes. So suppose if I consider this one is 100 Hz, this one is 110 Hz, this is 120 Hz, 130 Hz. Likewise, these frequencies if they are there, so then I can consider almost, because all of them are exposed to a particular vibration source. If a particular 100 Hz vibration is there, then this one will be giving you the maximum peak, and these values will give relatively low peak. But ultimately, when they are added, you will get a good amount of voltage. And the same structure you can use it for 150 Hz measurement as well. Because in 150 Hz, the another structure will give you the peak, the other one will be low. So when you are adding all of them, you will get relatively a flat bandwidth and good amount of power. Okay?
Bandwidth helps.
Bandwidth helps so that the same structure you can use it for multiple source. If some source is and it is not like that the ambient source, it will not be fixed at 100 Hz. Suppose some bridge, I cannot consider its frequency is always 100 Hz. Because it can vary between some 10 Hz to 120 Hz. Likewise, some variations can be there depending on at which frequency the vehicles are moving, how much force is being applied based on that. So, even if the vibration is not exactly same as your that structural frequency, then also it will be useful for generating larger power because its bandwidth is larger. So, for larger frequency range, it can be useful to give you the good amount of power.
For various sources, different sources.
Different sources, or even if one source with multiple frequency
But
constants.
and parallel simultaneously.
No,
Different sources you can get output simultaneously.
No, not simultaneously. This whole structure, suppose this is the whole structure where 10 cantilevers are there. So this structure where the vibration is there, you will mount there. If this is the vibration plate, the same structure you can use it in another place where another kind of vibration is there.
For another source.
Yes.
So not simultaneously.
No, not simultaneously.
But parallel
Yes.
output from the various
Yeah.
sources. It will be not. It will be not.
No.
Various sources.
Suppose-
Parallel output.
Here I have one bridge at place location 1. So there, suppose the frequency varying from 100 Hz to 150 Hz. I can install there, get the output. The same structure, if I have some other bridge whose frequency is suppose 150 to 200 Hz, I can use the same structure. I do not need to manufacture any other device. The same device will be helping you to get good output from this place as well as from that place. Not simultaneously. If you want to use simultaneously, you need to replicate this. 10 similar 10 arrays you will use. One you will put here, another you will put here likewise.
My question is not that. My question is simultaneously various different sources has implied on this system, and they will give parallel output for all the sources, and it will be somehow.
Now that if you want that, then you can do that. So then you need that, suppose 5 sources are there. So then you need 5 sensors to be put there. And then if you want, you can add them. So that is up to you. If you want to add all 5 together, that you can add them. But I am saying in one structure itself, suppose 10 beams.
Same structure, not for various sources.
Now same structure. So
This
now-
structure will be applicable for various sources, simultaneously inputting and simultaneously getting output.
No, one structure, how you can put simultaneous place? In the one structure you have 10 beams, so that you are putting here. So you are using there. If you want to put that structure in that place, you need one more device and you have to put there. And then if you want to add them, that you can do external. Okay.
Yes, possible.
So, yeah. So let us proceed further. So we can can add, if this Q factor is more, so then definitely that will give you the more overall power. So now let us move forward to the interfacing electronics. So we will start from the basic interfacing circuits and then we will move forward to the advanced latest interfacing circuits schemes. So in the interfacing electronics, what is there? Here you have the ambient energy. Here you have the harvesting structure like the piezoelectric or electromagnetic, triboelectric, whatever. Then you have the interfacing circuit. Then the interfacing circuit output, you will be storing it in some supercapacitor or rechargeable battery. Then you can put some regulator to regulate the output voltage at the desired level, and then you can use it for the powering the loads. Right? So that is the overall block diagram. Now let us look at, with respect to the piezoelectric or triboelectric vibration harvester, what we discussed. What are their basic interfacing circuits required? Because you know that vibrations is the source and the corresponding output will be also AC output. But normally to power the loads, normally we need some DC voltage, like some low power sensor, typically 3.3 volt or 5 volt. They are the typical load, that voltage requirement. So we need to convert that AC into DC. That is the simplest and most basic requirement. So what I can do, I can put this piezo triboelectric device. This is the simple bridge rectifier. Here I have resistor and capacitor, and here across this I will get the rectified out. So this bridge rectifier will convert that AC into DC. Then through this capacitor and resistors it will be smoothed, and you will get almost pulsating DC and kind of DC output, which you can connect it to some regulator and get some steady voltage, which you can use it to power up your loads. Fine. If I use this simple standard harvester circuit, that means if I don't use any interfacing circuits, only if I use the bridge rectifier and the resistor capacitor, then what issues can be there? If you look at this waveform carefully, so suppose what I said, what is the electric equivalent circuit for piezo and tribo? Current source in parallel resistance and capacitance. So that we can see. And now, if I have current source I, C and R is there in parallel, so what will be the voltage? I multiplied by the Z. Z impedance means R in parallel C. So that will be your output voltage. Fine. So if current is I and voltage is V, V means I into Z. So between the current and voltage, what differences will be there? Amplitude as well as phase, right? Correct. So suppose if you look at this waveform, this blue waveform, this is the current which is generated by the piezo or tribo device, and the green one, they correspond to the output voltage, which is nothing but the current multiplied by this impedance, and if some loss is there, so including those, the voltage is kind of this one. And there is basically the mathematical derivations are also there, that why this particular shape of waveforms you can get. That you can simulate also, simple some LP spice or that kind of simulation circuit also. If you just simulate some simple current source R and C parallel, and if you take the output, and if you consider I sinusoidal, the voltage output will be kind of this one. Fine. Now if I calculate the instantaneous power, so power means simply current into voltage you can multiply, right? Now if you look at, if you multiply this current into voltage and this red one correspond to the power plot, since there is a phase difference between this blue line and the green line, see that there is the phase difference is there. So if I consider till this portion, here the voltage is negative and current is positive, so positive into negative plus into minus, the power is becoming negative. From here to here, both are positive, so this power is also becoming positive. Again, from here to here in these portions, again this one is positive and this one is negative, so negative likewise positive negative sequence will go up. Is not it? So what do we mean? This is the instantaneous power, and overall power waveforms will include some positive half as well as the negative half. What is the physical interpretation? Physical interpretation means this piezoelectric transducer itself you can consider as a transducer which is converting the mechanical energy into electrical energy. So what is our requirement? I want to convert the mechanical into electrical. So positive means the power is going from the mechanical side to the electrical side, and negative means from electrical it is returning back to the mechanical side, which is not desired. So in order to improve the efficiency or improve the overall power output, what I need to do? I need to eliminate that negative power. What is the simplest solutions you can think of to eliminate the negative power? In order to ensure that always there will be positive power, we should have both current and voltage should be either positive or negative. In order to do that, what I need to do? I need to see where the phase difference is there. Accordingly, what I have to do? At that particular instant I have to detect and I will be flipping the voltage at that particular point. So suppose here you can see at this particular point the voltage is here, from here to here you have this voltage is positive and current is negative. So if I want to synchronize it at this particular instant, I have to flip this voltage here itself and make from positive to negative, so that in this portion both current as well as the voltage will be negative and the overall output is positive. So that I have to do, right? So this motivates the researchers to explore the interfacing circuits or improved interfacing circuit topology through which these synchronizations can be done and the negative power can be eliminated. Is it okay? Now let us move forward, and you must be interested to know how the circuit looks like, what kind of topologies we can think of to achieve this particular scheme. Before we move forward into details of that, and basically if you are interested, this energy return phenomenon and those things you can see from this relatively older paper as well. And yeah, so now little bit little mathematical equations, and basically in these slides we have shown this one as the theoretical concepts and just based on these paper informations and all. But the same thing, as I said, you can simulate it and you can check it. So that's why I have, for your reference, I have shown some simulations views as well. And this has been simulated in LT-SPICE. And here you can see, if you consider this blue one is the current, green one, this kind of voltage will be there. And if you multiply them, you can see positive and negative powers are there. So you can actually validate this as well. Now, so this is just the simulation aspect. Now just little bit conceptual things a little bit shown over here. Like basically, you know that as I said that piezo and tribo, they are basically the current source. So the current source means when the vibrations is there, what happens internally? The charge redistributions will be there, polarity redistributions will be there, and accordingly charge generations will be there, and because of that current and voltage will be generated. Fine. So this charge, if I consider that because of the vibrations some displacement is x, because of the vibration the displacement is x, then the charge generation that will be proportional to x. Q is proportional to x. If Q is proportional to x, what about I? I equals to dq dt. So I will be proportional to x dot. What is x dot? Velocity. X is displacement, so x dot is velocity. So current will be proportional to velocity. Now the voltage is again, there is the voltage sensitivity and charge sensitivity is there. So basically voltage in this case, simply this voltage is that other, in the other way voltage, that voltage is proportional to force or the displacement. So basically the current, if I consider x is the displacement, then current will be proportional to x dot. If I consider x equals to x cos omega t, then I will be proportional to sin omega t, and voltage will be proportional to cos omega t, and of course there will be some other phase difference as well as amplitude difference, and because of that these phenomena are actually happening. So this is the basic scheme, but the message what I want to convey is that it includes the negative power which we need to eliminate through some good circuits. Fine. And this piezoelectric is quite simple and reliable. We have already discussed about this limitation, that is the negative power, and overall it will lead to the efficiency degradation. So now let us discuss about the interesting topology which is called as synchronous switch harvesting on inductor, which is used to eliminate the negative power. So from the name itself you can understand synchronous switch harvesting on inductor. That means in the standard circuits we have only the piezo tribo and the bridge rectifier and RC. In between the piezo and bridge rectifier we will put one circuit, and what will be that circuit? You can think of some switch will be there and some inductor will be there. So that switch has to be controlled in such a way so that it will basically synchronize the zero crossing, you can consider, so that either positive or negative you will be getting. Fine. So now, and that has to be done synchronously, and accordingly the switch needs to be activated. The SSHA circuit will comprise an additional inductor L in series with a switch, and switch can be implemented by MOSFET or BJT, whatever. And the simplest scheme will be like this. So here you have this piezo and tribo. In between this piezo and the bridge rectifier, we have these mechanisms where we have one inductor and where we have one switch. What will happen when I need to basically how the switch needs to be controlled? It needs to see when those that zero crossing I need to match basically. Fine. So when the zero crossing is there, so actually that why in this previous slides I have shown the equation. Another reason is that with respect to the current, I need to check the zero crossing, isn't it? So when the current is zero crossing, at that particular instant of time, I need to flip the voltage from positive to negative, or at this point negative to positive, right? So with respect to current, I have to see the zero crossing. But normally when you are dealing with the circuits, you will be mainly measuring the voltage. So what about the corresponding voltage? The zero crossing of the current, that does not mean the zero crossing of the voltage. Why? Because current and voltage there, one is sine, another is cos. So zero crossing of current correspond to maximum or minimum peak of the voltage, is not it? So if I have current source, then with respect to the zero crossing, I have to detect the zero crossing and accordingly I have to flip it. But since conventionally we are measuring the voltage, so the corresponding voltage, if I want to see, then the maximum or minimum peak I have to see, right? So you can see typically this zero crossing correspond to this maximum peak, this zero crossing correspond to negative maximum peak, closely like this. And at that particular point we have to basically activate the switch. So when that will be detected, the switch will be on for a very small moment of time, so that this voltage will be instantaneously flipping, because you know that the current across the inductor will not be instantaneously changing, but voltage can flip, and that voltage flipping will be there when the switch will be turned on. And this turning on will be for a very small moment of time. For positive cycle, for one small moment of time it will be turned on. For negative cycle, another small moment of time it will be turned on, just to flip it. Once the flipping is done, then again the switch will be off and the circuit will go as well. Right? So this is the basic concept. Now we have to see the implementation aspect. The switch is turned on briefly when the mechanical displacement reaches a maximum or minimum corresponding to the maximum or minimum of the voltage delivered by the piezoelectric element. So with respect to current it is zero crossing, but with respect to the voltage or displacement it is the maximum or minimum peak where we need to trigger the switch. Right? As these triggering times, an oscillating LC circuit will be formed. So when the switch will be on, then here I have the L and here I have the capacitance. So LC oscillator, LC tank circuit will be created, and from the capacitance to inductor and inductor to capacitance, the energy will be basically go back and forth. And as a result, the overall Q factor will be also affected, and in this way it will eliminate the negative power and it will improve the overall efficiency of the circuits. So here this is the concept which we are talking about. So here you can see this is the current. With respect to the current, I have to ensure that at that particular time the voltage should be flipped from positive to negative, whereas at this instant from negative to positive, so that if you calculate the instantaneous power for this waveform, it will always give you the positive power. Fine? If it is clear, so then let us move forward. And what is our ideal requirement? Ideal requirement should be, this should be perfectly 90 degree. If there is some less than 90 degree, then again some small amount of negative power can be generated. So here is the circuit challenge and here is the research aspect, that how to reduce that time delay, because ultimately you are doing this through some BJT or MOSFET, transistor, inductor and some other kind of circuits. Another very important thing is that how to detect that zero crossing or peak and peak voltage. For that, you should not use some additional sensor and do the things, because ultimately you want your overall power consumptions you want to less, because your piezo tribo is there, some circuit is there, then some load is there, and load power you want to use it to drive some sensor or some loads. Now your circuit should consume as minimum as possible power, so that the maximum power it can deliver to the load side. Eventually the overall power is less. That is not desired, right? So the overall circuit complexity also you need to take into account, and the switching, you have to think of some switching mechanisms, some automatic switching mechanisms through which it will automatically detect these zero crossing things or maximum minimum, and accordingly it will activate the switch, right? So that's why here we have shown that although this is the ideal requirement, but practically there can be some small slope, and because of which some small amount of power can be still there, right? So till this point, if you have any question or doubts, please let me know with respect to this circuit concept. If it is clear, then we will move forward to the actual implementation. So if I use this SSHI, then it is giving superior performance with respect to the standard circuit. So this red one corresponds to the standard circuit where we didn't use this inductor and switch, and this blue one corresponds to the output when we are including this one. Eventually it is increasing the overall power. Just one representative power versus load resistance plot is shown over here, right? Now for these circuits, what are the important features and where are the research flavor? So important feature is that automatic switching. The switching you need to do automatically. In the circuit itself, some logic needs to be implemented which will detect this zero crossing or maximum minimum, and accordingly it will activate the switch. That you need to do. Second one is the switching delay. The delay should be increased or decreased? Delay should be decreased. Delay means the transition slope basically. That needs to be decreased. Next one is the inversion factor. So that means inversion factor means those from positive to negative and negative to positive, those basically the ratio which will basically eventually give, because ultimately you are converting it into the full bridge rectifier and finally DC output. So that what is the efficiency from the negative side to the positive side, this voltage divided by this voltage to give you that overall efficiency ratio. That is called as the inversion factor, and that value should be more. And the self power circuit. The circuit, for operating the circuit, you cannot use some additional supply. Then your whole purpose is gone, is not it? You cannot use some high power op-amp to integrate to realize this circuit, right? Because the op-amp itself will need some good amount of power. So those kind of things you need to avoid, and your circuit should be self-powered, so that, and self-powered as well as low power consumptions, so that it can give you maximum power delivered to the load side, right? So this is the concept of your SSHI based circuit and the important features. And there the storage and finally after doing that, we will be basically storing the energy. So how we can store it either through some discrete battery component which we can embed also in the harvesters, or we can think of the rechargeable battery or supercapacitor as well as the battery layers. Fine. So these are the basic concepts. Now we will see the actual implementation. Fine. So till now, if you have any doubts, please clarify. Now let us go forward. Let us move forward to understand one by one block that what is the concept and how this basically this automatic switching is done. What are the important blocks are required? So those aspects. So we need to implement this logic. So this corresponds to the piezo or tribo equivalent circuit, current, capacitance, and resistance in parallel. This is the SSHI part, switch and inductor. This is the bridge rectifier part, and this is the RC load, and from here I am finally getting the output. Now, here vibrations will be applied to the piezoelectric or triboelectric element, that will give you the output voltage. So what I said, when I need to activate the switch, I need to detect, if I talk about the current, then 0 crossing. If I talk about the voltage, I have to see the maximum or minimum peak. So what I need to detect the voltage profile. How the voltage profile is there, where it is maximum or minimum, that I need to detect. How I can detect that? For that, I need some voltage profile detector. And what else I need? I need the comparator, that whether I have reached my maximum or minimum value or not. So my reference is kind of your maximum value or minimum value, and the detector will be continuously giving you that this is the voltage profile. So those will be compared, and based on that comparisons, when the circuit will see that the voltage is basically, I have reached the peak, immediately the next switch will be activated, right, for a very small moment of time. Then again it will come back to its original position, and after that it is going to the rectifier and load, and subsequently the things will go on. So these are the blocks. Now we will see the actual implementation. So don't get worried by looking at the large circuit. Initially it looks, apparently it is quite complex, but when we will illustrate it, it will be becoming very, very simple and easier to understand. So just one by one let us move forward. So this is the piezoelectric equivalent circuit. No issue, current, resistance and capacitance. Fine. We told about this rectifier. This one is the rectifier. This one is the RC load, those things. So what is the actual circuit in my hand? This portion is the actual circuit, right? So this portion is the actual circuit. In the equivalent things, what we have seen basically, this one we have shown there, this one we have shown there. These things, inductor, switch and inductor, this portion is the corresponding to from starting from here to here, right? This is the block which is the interfacing circuit. Fine. Where is the inductor? This one is the inductor. Which is the switch? This is the switch. Now, if you look at these portions carefully, you can see this is symmetric with respect to this inductor. This with respect to the inductor, this corresponds to the left side and the right side corresponds to this one. Why these two sides are there? How many peaks we need to detect in one cycle? 2 peaks. One is the maximum, another is the minimum. Right? So that means one is in the positive cycle and another is in the negative cycle. And that you can see from the diode directions also. You can see that when the current is flowing from this side, in the positive cycles, the diode directions are like this. So these circuits will be activated in which cycle? Positive or negative? Positive cycle. Whereas in the negative half, the current will go from here, so that you can see the diode directions are there. So in the negative half, these portions will be activated. Fine. So to understand the circuit, what we need to understand? Only this part, if you know, that is sufficient to understand the whole circuits. Right? Now let us move forward. So what I need to do here in the block, what I said, that I need to have some detector, voltage profile detector and comparator. Right? So, and switch is this one. This one is the switch. And these transistors will be acting as the comparator. So this transistor diode assembly is acting as the comparator. This one is the switch. And these two additional things are there. I will explain that. These are acting as the envelope detector and voltage divider. Fine? How will it work? So, suppose let us look at the positive cycle. So, positive cycles, what happens? So, gradually the voltage will start from 0 and gradually you will be having this kind of profile. Fine? So, when the initially the voltage is 0, you can see how many paths are there in the positive half. This is one path and this is another path. Right? These portions will be deactivated because, and here from here also there is path, but whether the current will flow through this inductor or not, that depends on the transistor. If the transistor is activated, here it is NPN transistor, if the BB is more than 0.7, then only it will be activated, otherwise not. Right? So initially this transistor is off, so switch is also off, and now gradually the voltage is starting from 0 and gradually it will move to peak, then it will again come down. So what is happening? When the voltage is produced, you can see through this path, the capacitance will start charging. The capacitor will start charging. Fine? And this VC1, that is the voltage across the capacitor, that will gradually build up. Another path is this one. Here we have another, that voltage current path is there. So in this case, at this this voltage we are giving the name as VR3. VR3 is simply this voltage minus this diode drop, and that we are connecting to the base of the transistor, and this VC1 is connected to the emitter of the transistor. Fine. So this is one PNP transistor, and PNP transistor, when it will be activated, when this VE will be greater than VB by 0.6 or 0.7, right? Initially, when the voltage is gradually increasing, what about which voltage will be more, VR3 or VC1? VR3 will be more. Why? Because capacitance needs some time to charge, that build up the charging, is not it? So basically, this VC1, that will be lagging this VR3 in initially from what position to what position? From 0 to V peak. From 0 to V peak, capacitance will take some time to build the charge. And here this voltage is simply subtracting the diode voltage. Here you have this VR3 which is connected to the base. So initially, from 0 to peak, 0 to positive peak, which voltage is more? VR3 is more than VC1. So what about the transistor T1, on or off? Transistor is off, because this base voltage is less than emitter, and this is your PNP transistor. So when it will be on? When this VC1 will be more than VR3 by that 0.6 or 0.7. When it will happen? So this capacitance will take some time to show the charge build up. When this VR3 has reached peak, and after that VR3 will reduce. When it will be reducing, then this VC1 will try to reach that peak value. So for a very small moment of time, when this VC1 is more than VR3, at that particular time instant, this transistor will be turned on. As soon as the transistor is turned on, it will be basically through this path the current will flow, and this transistor T2 will be also turned on. As a result, what will happen? There will be a path. In this path is now that closed path, because transistor is on and current will flow through this inductor, and then what will happen? One loop will be created. One loop is between LC and this CP. LC and CP, one tank circuit or oscillator circuit loop will be created. Another loop will be created between LC and C1. Fine? So at that, as soon as it is dipped, then again immediately these transistors will be turned off, because again this voltage will be more than this, and the transistors will basically turned off, because here this voltage has been now going to the negative side. And negative side means by default these particular transistors will be turned off, and in the negative path, this path will be activated, the current will flow in this way. Here again you can see, here you have this capacitance charge, this is your VC2, and here you have this VR4 you can consider. Here again this is your NPN transistor. So initially these transistors will be turned off, and then when the negative peak will be there, then this will be turned on, and eventually the LC. So here you have this particular transistors will be also turned on, and then the LCCP loop will be created. So in this way, this particular circuit is working. Fine. Now this is basically, this particular circuit topology was proposed by the researcher in around 3-4 years back. The initial SSIG circuit is relatively older, and this particular is some advancement of that circuits. Now what we have done, so here also we have tried to improve some modifications to increase the overall performance. How we have typically done that? Here we have basically, so here what we need, here we have a VC1, here we have VR3. So this difference, VC1 and VR3 difference, you should have, suppose when your VR3 has reached peak, then VC1 does not reach its peak. When VR3 will come down, then VC1 is reaching its peak. So how quickly that VC1 can reach to the peak? If I can make that thing quickly, then at that particular time instant I can get very sharp transition. So I need, to reduce the switching delay, and also I need to synchronize that at this particular peak I need to basically flip from positive to negative or negative to positive. We should have some kind of modifications. So that's why we have put some extra voltage divider circuit over here and through one resistor and diode combinations in order to reduce that time difference, and we have seen that by incorporation of that I can reduce the switching delay. Even I have put one resistor, and by changing that resistance even I can get the perfect zero switching delay as well. So some results we will show. So I hope the basic operations is clear to all of you. Is it fine? If yes, so then same what I have explained that is written over here, that explanations of this envelope detector, voltage divider, comparator as well as switch. Yeah. So if it is clear, so now let us move forward to give you some glimpses of the ongoing research activities, and as I said, I will start from I will try to give some chronological perspective, so that, and this particular work just around 5-6 years back I have started to work on this area, and just how we have started. So starting from the scratch I will discuss, so that it may be helpful for you also to plan this kind of activities, or definitely as I said you can do even better than that, but it will give you some kind of reference or benchmark. Fine. So as you have seen that I am basically affiliated to this Advanced Technology Development Center at IIT Kharagpur. So this is basically in this center we are mainly that we do a lot of interdisciplinary research activities. So as far as the academic program is concerned, so we have currently 2 M.Tech programs. One is on embedded control and software, another is this electric vehicle, and we have a couple of faculties in mostly in electrical and computer science background. Apart from that, we have as regular this masters and PhD programs are there, and some undergraduate, dedicated undergraduates are not there, but we have some micro specializations on embedded control and software, right? So, and there the lab which basically we have developed is that names Embedded Electronics and Energy System Lab. So with respect to that I will discuss. So of course, as I said, I started working after the my PhD topic is little different. So here I have started just after my PhD, and when I have initially joined at IIT Kharagpur. So there from we have started. So that's why just I will start from some glimpses which may be helpful to you. So first of all, to start working on these topics, first I thought that okay, that theoretically people have done, but some things experimentally we should show, and experimentally once we convinced that okay, that really this concept is working, then only we will move forward to that investigate further. Otherwise, if it does not have any impact, so then there is no point of putting effort and time, right? So initially we started with okay, that to test it, we started with some that from experimental aspects basically. So first of all, we thought that okay, that for vibration energy, let us consider the piezoelectric, and let us first start with how should I test it? Because vibrations where from I should generate some laboratory skill, I have to do it. So first of all, we have started with that what should be my piezo. So we have just seen a couple of different piezo variants, and this one is the piezo materials which we have chosen in the beginning. Later on, we have shifted to another material which is having more sensitivity. So we started with this one. What next? Next we thought, okay, how to test it. So to test it, we need some, people have reported very high cost vibration seeker. So that was suppose even 10 lakhs or more than that to develop the setup. So okay, so initially at the beginning of the career, so it is difficult to get those fundings and all. Right now we have all those equipments are there, but initially we thought how to start with that. So what we did, we simply consider the speaker based arrangement. So speaker we have used as a vibration source initially. Fine. So this speaker is there, and we will be what we need to use. We need some function generator, and we need some power amplifier, because directly the function generator cannot drive it. Because typically, what is the speaker resistance? 4 ohms, 8 ohms, that kind of resistance. We need some power amplifier to meet the power requirement. So what we did, simply we use the speakers. Initially, some very small speaker we have considered, and here some arrangement we have made with some fixtures and all. This is, of course, we started at IIT Kharagpur. And then here, this is some cantilever beams are there, just simply aluminium plate, and here we have put this piezoelectric structure. And just we have started this is the typical block diagram. Like here we have this speaker is there, power amplifier output is going to the speaker. Here I have function generator, that output goes to the power amplifier, and from the power supply I am giving the power amplifier output requirement 12 volt or so. And then here I have this that some sensors and piezoelectric device we have used to see its output in oscilloscope. Just to check initially. This is very preliminary things, but just I thought let us start with this. So this is just a simple setup like the cell speaker setup we have shown. These are power supply, function oscilloscopes to and they are connected to the power amplifier, and then it is going to the speaker, and as per the given vibrations it will be moving. But of course we cannot generate the vibrations as per our intent sensitivity, because speaker itself is having some resonant frequency and very low frequency you can test. Hardly some maximum up to 20 Hz, 30 Hz you can go with this, not more than. Okay, so let us start with that, and initially of course we started with some conference communications. So then this is the whole setup. So as you can see, this is your this I will explain what is that. So this is the speaker based setup on which some structures are there. This is the function generator, this is the power amplifier, this is the connections. Here we have some power supply, oscilloscopes and signal conditioning circuits. Some initially we started with simple bridge rectifier, and then here is the load. And here just to see, this is the raw piezo output and this is the accelerometer output, just to check whether, here I have put some accelerometer also just to check basically that whether to verify the characteristics of the piezo, whether the frequencies are that properly matching or not, or the required frequency I am getting or not. So those things just to show that. Then simply from this piezo we have connected some bridge rectifier and some load resistors. We have got something 0.78 milliwatt kind of power, 782 microwatt. And this is just the very initial work and initial setup. So then based on that, so then we thought of some ideas and activities, and based on that I just applied in that ACRB for that startup research grant. That at that time it was early career research award. So I came up with some proposal based on this cell port sensor application using energy harvester, and based on that in 2017 we got one project funding from ACRB, and we started working on that. And then we gradually procured the equipments and carried forward the activities. So parallelly we thought of that, okay, if some that MEMS versions or basically miniaturized versions if we want to do, then how to do that. And with respect to that we thought of, okay, that as you remember that we have shown that what are the different important features based on which it depends the performance improve, basically on which the performance depends of this piezoelectric or those kind of energy harvester. So there are one aspect we told about material, second aspect we told about the design aspect. So as far as the design aspects, the very simple structure everyone use is the standard cantilever configuration. We started with cantilever configuration, then we tried to put some modifications very small one by one. So what we did with that, based on our some previous experience and some that literatures, what we have seen that on the cantilever itself, if I incorporate some perforation or hole, then what will happen? It will eventually reduce the overall resonant frequency of the structure, and if the resonant frequency reduces, that will lead to larger power improvement. So with respect to the design aspects, simply we have considered one hole on the cantilever structure. So this is the clamped end, this is the proof mass end. We did some theoretical analysis as well as the simulations, and finally we did some experimental analysis as well. So we have just initially started with some miniaturized MEMS dimensions, because I had some previous experience on MEMS sensor design and development. So there are some like some 1 mm, 2 mm kind of dimensions we have chosen, which can be fabricated using MEMS technology, and then some holes we have created, and then we have just seen that we started with some square hole, and just some examples are shown like the power versus load resistance, and these graphs correspond to different size of the holes. So this as the size of the hole increases, as you can see this lowest one is the without hole, and as the hole is incorporated, as the hole dimensions increases, gradually your overall power improvement is also happening. So based on that we started the design aspects. So then we have done some optimizations of the holes, what should be the optimum dimension. Because what happened that on this structure your piezoelectric device will be also deposited. If the hole size is more, then definitely your resonant frequency is reducing, power is increasing. But at the same time, if that large hole is there, eventually your piezoelectric material is also less. So less piezoelectric material means that will give again less output. So that's why there is some trade-off, or basically we have to think of some optimization, that what can be the maximum hole dimensions I can choose. So accordingly we carried forward the things. So then this is some layout basically with respect to when we want to design the MEMS-based device. So for fabrication purpose we need to design some layout also. This is some layout design is there depending on what process we are using. That is just for some information purpose. Now next we move forward to the further design analysis and simulation aspects with respect to the performance improvement and some kind of optimization aspects as well. So we started with some theoretical analysis initially. This is the whole cantilever, this is the mass, this is the whole dimensions actually. So we can basically calculate theoretically also using Rayleigh's method energy, that technique, that by taking the ratio of your kinetic energy and the static energy, we can get the resonant frequency. And if I incorporate these holes, so then how the resonant frequency is affected, so those analysis we have carried forward, and the detailed derivations can be found in those published papers. So here basically this is just how the hole is affecting your overall resonant frequency, that point.
Sir, did you consider single hole or multiple?
Yeah, initially this is the single hole. Okay. So
Or the hole in any other places or any other, you have hole on the tip.
no, this is not the tip. Basically, this is the anchored region,
Anchored
and this is the free region. So
Okay.
we have basically considered this and varied. So here, what can be the parameter? One can be the dimensions of the hole, another can be the location of the hole, another can be the number of holes. So these are the three main parameters. So we have basically tried to do the analysis for all of them and try to see what can be the kind of optimum.
So single hole
designs.
is the best.
No. So mainly that single hole and that dimensions we have optimized. We have also seen for 2-3 holes, but in that case your overall analysis complexity is theoretically it is a little bit increasing. So those things we have done it in some simulations mostly. But for the single hole we have derived the corresponding theoretical analysis as well.
Which simulation tool you are using?
So for the simulation purpose mostly these are done in COMSOL multiphysics. And for analysis, for different mathematical analysis, the different equations are referred as per the requirement. But for the simulations points, mainly we have referred the COMSOL multiphysics.
So hole should be square shape or maybe a circular?
No, we have seen for rectangular as well as circular shape also. So for them, all of them, the optimizations as well as the experimental validations are also done.
Which is more advantageous to reduce the resonance frequency, a square or?
No, we have seen that, suppose we will show that. So if I take some rectangular hole with a particular length and width can be like this only, then we are getting that maximum optimum value. So rectangular hole mostly based on the optimizations we have got the rectangular hole with a certain dimensions.
Okay. So this is the same occurring as we have studied in the energy meter that we are keeping on hole on the disk.
Yeah, creeping those.
Creeping effect to reduce the creeping effect.
So now here this is basically kind of mechanical structure point of view. So it is mainly that this here in this case the whole job is to reduce the resonant frequency of the structure basically, because the power is basically inversely proportional to the resonant frequency. If it is less, so power is becoming more. So with respect to that mechanical design perspective which has been put here. Okay. So now here just some COMSOL simulations are there, like this is the cantilever, here some mass is there, and here this is the piezoelectric material basically. So just some examples, like we have considered some rectangular hole, circular hole, and we can see the analytically as well as this finite element analysis based tools, as for different holes the resonant frequencies are increasing, and if we compare between analytical and these simulations, they are quite close to each other. Hardly 5%, 10% maximum error we are getting between the theoretical and simulations results. So then we carried forward the simulation and analysis. So here you can see that if we plot the stress versus length, because in order to get more power the stress variation should be also more. So here you can see the red one corresponds to the circular hole, there the stress variation is more. So even accordingly the circular hole is expected to give better power for the overall harvesting point of view. Then we have done the corresponding experimental validation. So on the same speaker setup, we have basically put this aluminum plate here. We have created some hole. Here is your piezoelectric device, and that subjected to the vibrations. And for different holes, we have carried out the testing. So here in this case, we have without hole. Then we have put the rectangular, rectangular hole or square holes. Here we have the circular hole. And based on that, we have basically seen for all the cases, we have just carried out the experimentations, and from the piezo how much power we can generate after connecting it to the simple. So till now we did not use any advanced circuits, only the simple rectifier circuit and RC circuits we have used this. Because initially we worked on the simple structure and the design perspective. So here again you can see that voltage versus frequency. In this case also that theoretically our circular was giving better response, but here we can see that the rectangular is relatively high than even the circular, and red one corresponds to the without hole condition. So without hole we are getting something for the 4.5 volt, where if we incorporate this holes, then we are getting around 6 to 7 volt like this. Some initial improvement we have seen initially. So after that, just some few comparisons between simulation and experiment, like in this case, simulation versus experiment, whether our simulations or this theoretical is correct or not, to validate that, and also in order to validate it with the experimental setup. So just some, you can see that theoretical versus simulation versus experiment, and definitely you can see that there are some good amount of deviations are there, because it is not very easy to always validate the exact your simulation things with the experimental, because of the environmental, because lot of different, suppose for this case we are using COMSOL multi, so that you may not be able to incorporate all the required constraints or that required parameters in order to give the exact output. So that's why definitely there are a lot of scopes to improve the simulation platform as well as the theoretical techniques also, but definitely that will be more complex. So this is about some of the simulation experiment. This is again, then we move forward to the optimizations part. So till now we did not touch the optimizations. Now we have moved forward to the optimizations of the hole dimensions. So here some without hole, here some random hole, and then based on the analysis we have got that if I have this kind of rectangular shape with a particular length, then only I will be getting the optimized output. Beyond that, if I increase the length, then the power is reducing. So that kind of things also we have carried out. And here basically this ratio, that what is the overall length of the cantilever and what is the overall length of the hole. So that ratio we have basically optimized, and for a particular ratio only I am getting the maximum output. So those study have been carried out. So here just this kind of expressions we have arrived after based on the optimization techniques. Here some dimensions are shown, some small dimensions structure we have considered, and like the optimized hole, if I consider the length of the cantilever as 1200 micrometer, that is 1.2 millimeter, and length is 0.25 millimeter, then the optimized hole dimensions is coming around 0.48 millimeter cross 0.125 millimeter. So that is kind of the optimizations dimensions of the holes which we have got. But of course, to arrive at that dimensions, we have to think of some design constraints as well. So some constraint we have put, based on that we have got these particular dimensions of the holes for which we are getting the optimum performance. So here some optimizations flowchart is shown, which we have followed to get the optimizations scheme. Very simple schemes we have considered, not very deep mathematical views. So what we have considered, simply we started with some dimensions, then we have done some FEM, that simulations as well as the analytical solutions to get the resonant frequency, and then we have seen if the resonant frequency is very large, so then that is of no use, because typically the ambient frequency is quite low, right? So we have seen that for a particular frequency, in this case 5 kHz is set, because if I talk about the less dimensions, so then frequency will be more. If I want to get 100 Hz, 200 Hz, your dimensions of the structure should be more, right? So since yet we are dealing with the MEMS-based device, so we have started with some simple kilohertz. We have set some kilohertz range frequency. If we have achieved that frequency, then we have gone to the optimizations. Otherwise, we have tuned the design further to reduce the overall resonant frequency. Once we get the overall resonant frequency, then we have incorporated the holes, and in the hole you have location, length and width. These are the 3 parameters. So all the 3 parameters you cannot change simultaneously, that will lead to more complexity. So we have just put one by one. Suppose location is constant, then width is constant and length is varying. So likewise these different cases are considered, and based on that we have arrived at the particular dimensions of the holes which will give the maximum performance. So based on that we have got some, suppose as you see this, as the hole length is increasing, your resonant frequency is decreasing and the resulting power is also increasing. So ultimately we have come up with some ratio factor, hole length versus cantilever length, and here voltage versus this factor and power versus this factor has been plotted, and you can see in this case we are getting that ratio around 0.2, near about 0.2 we are getting that larger optimized performance, because above 0.2 the power is reducing, less than 0.2 also power is reducing, so around 0.2 we have got that ratio for this particular structure. And in this case we did not put any end mass on the tip of the cantilever. Then when we put the tip mass on the cantilever, then the same analysis we have carried out, and in that case the different ratio we have found. In that case around 0.4 is the ratio for which we are getting the optimum power. Right? So these are some of the representative results to give you the idea about this the design optimization activities which you have started in the initial. Fine? If you have any doubts, you can ask me. Huh?
Which software is used?
Which?
Software is
Yeah. So for simulation, COMSOL multiphysics is used. Yeah, COMSOL multiphysics. So now just to show you some idea, as I told that some MEMS versions we want to do for that. We have just some simulation results like eigenfrequency, stresses. So those you can see from here, and this is kind of the layout. So layout means that once you are designing it, after the design, once the design is finalized, then you have to do the layout, and that layout you have to send it for the fabrications. Where from the actual fabricated device you can get, or if you have your own process, own fabrication process are available, you can do it as your own also. But for that, this is the mask design or the layout design. Fine. So yeah. So next we have tried to see some other kind of modified structure. So initially we have mainly focused on the design part. Then we have moved forward to the circuit part. So in the initial design part, then again some kind of meander structure, meander shaped structures we have considered for to be used as both for sensing application as well as the energy harvesting application. So sensing means typically we have considered that acceleration sensor example, which is nothing but your mass spring damper system kind of things. So half meander means in this case this is the conventional half meander structure. Means that this is your mass and these are the two springs, straight springs. Now, what is the modified version? And here basically this is the spring and this is the mass. So this is nothing but your mass spring system, which can act as your some acceleration sensors or some kind of that energy harvesters applications as well. And this is the full structure where we have, this is the mass and both sides we have 2 to 4 springs. Now, what design modifications we have done? You know that if I want to reduce the resonant frequency, the stiffness has to be reduced. So the spring needs to be more compact. In order to make the spring more compact, the length needs to be increased. But straightforward spring you cannot use. Then it will take larger space to increase the length and reduce the frequency. So what we have done? We have just used this kind of serpentine springs. So instead of this straight springs, these are the some serpentine springs are there, and this is the small mass is there. Similarly for this case, this middle one is the mass, and these are the 4 serpentine springs. Fine. And for this case, if I want to use it for the acceleration sensor example, so then simply this is your mass, this is your spring, where it will be exposed to vibrations, it will give you the displacement, and you can convert it into voltage using circuit. That is for the sensing purpose. But the same device, if you want to use it for energy harvesting application, then what you need to do? You need to deposit on these springs, you need to deposit the piezoelectric, because the springs will be subjected to stress variations when it will be exposed to vibration. So accordingly the piezoelectric will be deposited there, and you can basically calculate what is that extracted energy from that. So based on that, we have basically again carried out mostly some simulations as well as some analytical views, and to give you some plot of that natural frequency as well as the stress variations, and based on that we have basically For the sensing point of view, we have just calculated its sensitivity, acceleration versus output voltage. So here you can see that this is the half meander shape. So this we are calling as the half meander, this we are calling as the full meander. So this you can see in both the cases, this black one correspond to the that design structure and red one correspond to the conventional structure. So with respect to the conventional structure, we can see that larger sensitivity we are getting, the slope is more, so the overall sensitivity is also more. And also these structures we have used for the energy harvesting applications, where basically on these spring regions we have deposited the piezoelectric material and we have seen the output voltage performance. So since in this case we are dealing with the miniaturized versions, so of course the power is also less, some microwatt range. But to increase the power, mainly you have to go for some macro scale design. So just to show you some plot that here this power versus load resistance, some optimum plot is shown for this two meander design. And here in this table you can see this column corresponds to the conventional structure. This is the half meander modified version. This is another conventional. This is the modified version of the full meander. In all the cases you can see the resonant frequency is less in our that design structure with respect to the conventional one, and the overall sensitivity is more, power is also more in the design structure with respect to the conventional one. So these are some with respect to some design perspective, right? So these are about the piezoelectric, and mostly till now we have mainly discussed about this piezoelectric device. They are mainly the design point of view, right? Now we have also moved forward to the triboelectric device, whose illustrations we have discussed. So initially, with the same speaker setup with the larger speaker we have arranged, so that with that speaker we have made some arrangement that some portion is fixed, that is connected to the speaker base, and another is connected to the diaphragm of the speaker, so that this one will be fixed and another will be moving. Like this kind of contact separations platforms we have created, and again through that function generator or the power amplifier we have triggered the speaker to generate the required vibrations. Here again, initially for the tribo, as you have already discussed, its principal contact separation based, and some output voltage versus displacement, some plot is shown over here. So initially some that console simulation is done, then some experimental validations have been done as well. So here again this is the setup. So as you can see, this is the speaker based arrangement, and these are the fixed portions. So here we have put one plate and another plate is connected to the diaphragm, so that the diaphragm will be moving and the plate will be touching to each other, and the corresponding output you can get from here. So this is just to give you some idea that this is the typical, you can see that speaker is vibrating, and with this low cost speaker itself you can generate that setup, and this is the typical triboelectric output. So then, so after that these are some of the experimental output. As you can see, some pulse you are getting, but the average and these pulses, although these voltages are typically 20 volt, 40 volt like this, but since the pulse width is very low, it is bit difficult to extract the effective power from it. So nowadays, that in addition, that with respect to the energy harvesting point of view, the triboelectric definitely have some impact, but more than that, the sensing point of view also we use this triboelectric device. So sensing means, suppose that can be used to detect some vibrations by measuring its output, or also suppose in some ocean wave applications, wind wave applications, different kind of applications also we can use it for the sensing purpose. Now, so till now we have done the experimentation on the speaker because we didn't have the fund, but after that we have procured the corresponding vibration shaker, and where dedicatedly you can even from that DC to up to 4 kHz, 5 kHz, you can generate the frequency in very controlled way. So this is one of that vibration shaker. So here they have dedicated power amplifier, controller, those things are there, and here the tribo setup is shown. This is that lower plate and this is the upper plate. So this plate is connected to the shaker arrangement and it is moving and it is basically touching this upper plate, and this is again another setup with respect to the triboelectric. And where we use this dedicated setup, and this is again another harvesting structure with another setup. You can see this is one that wooden structure which is fixed, and here bottom one, this one is the shaker body where we have put the another plate, and that shaker platform is moving and that is contacting with this upper plate which is mounted on the bottom of the wooden plate. So then you can see when we are exposing that same tribal in this controlled environment, you are getting that rather relatively better output in the sense, and here even that output, this peak, that although it is spike kind of things, but it is more regular because here with more controlled environment we are activating this, and in this case the overall average power is relatively far better than those speaker based setup. But the initial setup or arrangement you can definitely do with that speaker as well. So after that we have also done some kind of simple solar cell based that activities, and in the solar cell a lot of people are using or working on the solar cell, but our focus is little bit different. Here initially we tried to work on this efficient dual control scheme with output voltage regulation and MPPT for that photovoltaic system, where we tried to come up with some simple control scheme which will that regulate both the MPP maximum power point as well as your output voltage. Both will be regulated together with a simple PI control based scheme. So that is just one part of that work basically. So here you can see that initially we have this is the solar cell, some very small solar cell is there, and initially in lab environment with this simulator kind of arrangement with this bulb setup we have done, and then later on it is mounted on the roof and we have got the output. So this is just to give you some ideas that here just you can see the duty cycle ratio is changing, and here basically this 3-level boost converter is used here as the power management circuits, and using that we are trying to basically drive some simple fan nodes or some sensor nodes. This is just one small part of the work related to the solar, but as I said here our main focus is on this dual control scheme, and later on we want to integrate this solar with those other vibrations part as well, so that you can have some kind of integrated system. And this is just, you can see this voltage is regulated like 15 volt, although when the load is changed, so some spike is coming, but more or less you can see that steady voltage is maintained, and here power is also around 3 watt power is maintained, so both the voltage as well as the power are controlled, and definitely these blocks will include different as I said that your 3-level boost converter is there. In addition to that, some power hysteresis control loop is there. Along with that, the simple PI control logic for this voltage control. So then, initially you have procured this small shaker basically from this model shop, where it is having its inbuilt power amplifier. Only you need function generator to basically drive it, right? And on this we have mounted the PCB, and this here you can see this is the piezo has been changed. Here we have used this piezo. This is something PPA 1011 and 1014. This kind of piezo we have used. This is the piezo. This is the corresponding PCB that is for the cell pod application. So basically with this PCB we have incorporated the SSH, the power requirement of some low power sensor. Like you can see, this is your piezo device, this is the interface circuit, and this is the accelerometer sensor, which is powered by the energy which is extracted from the piezo. It does not have any other additional power supply. All the supply is provided by this piezo output voltage itself. And you can see this is the SSH circuit output. So you can see almost very perfect. It is not perfectly 90 degree, but still you can see very good transition is there in this zero crossing, which is the output of the developed circuit. So now these are of course some of the ongoing activities basically. So here again this is the one of the setups. So this is the initially this was done in the breadboard, that board, and then the PCB was designed. This is the shaker, this is the function generator, and the oscilloscopes are there. So here again some that representative experimental videos you can see. So this is basically the shaker is excited, and so you can see some of the so the vibrations you can see, and here just the output of the SSHI based circuits. Here you can see different kind of outputs in the positive side, negative side, inputs. Those are plotted just to give some demonstrations. Then we have so you can see this vibrations of this structure, and this is the excitation signal which is given to the shaker basically to make it operate, and this is the typical output. So this yellow one corresponds to the rectified output, and this pink one corresponds to the accelerometer output, which is basically powered by the PU device. Here we did not use any additional supply, so all the power is generated by the piezo along with its the corresponding circuit, right? So now here some experimental analysis we are showing, like this is the raw piezo output. You can see around even 55 volt peak to peak raw output we are getting. But definitely the problem is that even if the open circuit voltage you can get 50 volt, but as soon as you connect it to the load, it will suddenly drop down to even 10 volt, 2 volt kind of things, depending on the load requirement. So that's why you should have good that circuits as well. So here you can see these two plots correspond to the switching delay, to show the switching delay. Here you can see that this yellow one correspond to the excitation, and this one, this nearly blue color correspond to the output of the SSHI. So here you can see that this, although it is not visible clearly, but in these portions the sharp transition is happening, and the switching delay is reduced by choosing the proper modified circuit components. So with respect to that, we have varied or carried out some experiment to show that switching delay can be reduced. Here some other waveforms are there, like this is the input, and yellow and pink violet color correspond to that two output, and this is the final rectified output voltage. Around 12 volt we are getting, and around, in this case the harvested power is around 1.5 milliwatt, right? So that from the layman aspects, although we may think that how much it will matter, simply this 1.5 milliwatt, but it matters a lot as far as the low power applications are concerned, or some low power sensor nodes we need to drive. For them it is more than enough, because hardly they draw the current in few microampere range. So this is some of the experimental analysis. These are some ongoing work. Then again, as you can see this, if I increase this R nu value, one R nu or resistances we have incorporated, by that the switching delay is reducing significantly. So that is to show you, that give you the idea that by modifying the circuits we can reduce the switching delay, so that the overall power can be improved. Here some comparisons are shown, like if I some power calculations, like if I use standard circuit without any SSHI, then something 400 microwatt we are getting some average power. In the existing work, what people have reported in SSHI, they are getting around 1 milliwatt, whereas for our this case we are getting something around 1.14 milliwatt. So that definitely can be that improved further depending on the further modifications in the circuit. So that is with respect to the circuit activity. So now we have moved forward to the hybrid harvester concepts, where these multiple transduction mechanisms we can hybridize together. So like for example, if I consider that piezoelectric, thermoelectric, electromagnetic, solar, we can integrate all of them, and we need to have some suitable interfacing circuit. Then we, using all of them together, we can store the energy through some battery or supercapacitor, and finally we can use those energy to power up some smartwatch, robotics, and other IoT that sensor nodes. So that is the concepts with respect to the hybrid harvester, so that at the same time we can extract energy from multiple sources, which can be used to power up the devices, that low power devices. So here this can boost up the overall harvested power, and the several applications, like you can consider the human health monitoring, structural health monitoring, your intruder detection, self-power system development, and so on. So followed by that, we have basically tried to hybridize this electromagnetic and piezoelectric together. So basically this electromagnetic, this we have designed using simple 3D printing techniques. So what we have done, we have designed this particular structure using 3D printing, and you can see there are different slots are there. Inside this we have put these magnets, and in these slots we have wrapped around the coil. So when, and there are two caps are there through which you can seal it, and if this whole structure is vibrated, so there will be relative displacement between magnet and coil, because of which across the coil we can get the output voltage. So this is the setup for that electromagnetic harvester. So as you can see, this is the electromagnetic structure, this is the corresponding circuits, and this is the whole setup. So then just that here we have shown that when we are combining this piezoelectric and electromagnetic together, So suppose initially this output voltage corresponds to only piezoelectric. This is the final rectified output, and at this particular instant we have incorporated both piezoelectric and electromagnetic together. So you can see the output voltage is basically increasing from this value to this value. In this case, around 1.24 volt amplitude we have extra voltage we have got because of the additions of this electromagnetic. But definitely that can be increased further. To give some further output, you can see that here just the charging time is shown. In the load we have put some capacitor and to show the charging time. If you use only piezoelectric, you can see this is the charging time. It is around 18.52 seconds from one value to another value, and to reach to same value, if I use the hybrid harvesters, then you can see it is taking only 12.84 seconds. So this time interval corresponds to the hybrid 12.84 seconds, and this corresponds to the only piezo. So you can see we are significantly reducing the charging time also, which is eventually increasing the overall efficiency of the circuit. So then finally we are showing some self-powered applications. So like demonstrations of piezoelectric based self-powered accelerometer sensors. So this one, I think we have shown it. So here what we can see that because of this yellow one correspond to the final rectified voltage, and pink correspond to the output of the accelerometer, which is driven in self-powered way. Then that is only with piezo. Now when we are basically using this piezo and electromagnetic together, so you can see this piezoelectric is vibrated from the vibration seeker, and initially this electromagnetic is hand vibrated. So then based on that we can see it is more output voltage we can obtain, and it can drive the accelerometer for longer time. Then so this one we can see this is the simple small solar power based device. So here you can see through that solar power, so some values are just shown, and we can see that loads are there. So just to show very small, some this fan is moving when we are basically activating that solar cell. And finally we have so this is to show the charging time whose response we have shown. Basically the charging time for piezo and electromagnetic together, the charging time can be basically optimized and reduced. When the electromagnetic is used, the charging time of the capacitance is reducing, and that is eventually leading to more better performance. Right? So these are some of the self-powered applications with respect to this ongoing activities. So I hope till now it is clear. Any doubts if you have, you can ask me.
So vibration energy can be stored without battery.
No, some storage you require, because the vibration energy you are getting some, you are converting the vibration energy into electrical energy using the transducer or the circuit. But finally, without storage, if you that something is required to give the power required. So at the end, even you are using a simple capacitor, that is also nothing but storing that energy, which you are using.
Vibration is the mechanical form is to be transferred in another mechanical form which can be used as a potential energy. Again then, when I am required, it will be transferred to electrical energy.
Okay, so that...
is there any arrangement is so far research has been done?
That
vibration to mechanical potential energy.
Yeah, I understand. So some vibration is there, you want to store it, and whenever it is required, you want to use that kind of...
In electrical form.
Yeah, so that right now, I don't think that is there, maybe something is there, but that if you want that electrical energy, like we have some storage devices there, but vibration energy, like normally we know that static energy, those simple spring arrangement, static energy is there, then again when it is removed, it is
change of the
deformation
of the spring we can do.
Yeah, so that
vibration
kind of,
can be changed, the deformation of the spring, in that way we can.
Yeah, that is kind of one conceptual things, but if exactly some scenarios is there or not. So right now I am not aware. So if, but as of now I am not aware of that. So maybe something can be there. Okay. So finally let us discuss about these self-powered systems and applications aspects. So self-powered system concepts is very important and novel power supply technology. It can be eligible to power up loads situated in, as we said, remote infrastructure locations. cell power system can be designed either individually or in hybrid mode. And several applications like cell power wireless system, wearable electronics, robotics, we can see. Just two examples I have taken from some so the energy harvesting piezoelectric structures are there along with that circuits, and that energy is stored and that is used to analyze that if suppose some gate or basically abnormality detection of some persons, or how is his body activity is there, so those things are being monitored, and for that the power is generated by the energy harvester itself. So then some another systems like where triboelectric and biofuel cell hybrid structure is shown, where basically in the body the triboelectric structure TEG as well as the PFC, that biofuel cell structure BFC, those are there. And what they do, so this triboelectric based on the vibrations of the body, and biofuel cells that is based on the sweating of the body, those chemical analysis point of view, they generate the energy. And as you can see here, simply this triboelectric generator and body fuel cell, their output is used to charge up the supercapacitor which is stored, and then they are used to power up, meet the power requirement of different wearable electronics. Right? So these are some of the cell power system examples using the energy harvesting concept. Right? So these are the majority of this topics which we have covered today. So we have started with the basic background understanding of the energy harvesting technology. So we have started from the very beginning, its importance, its requirement along with the application. Then we have focused on different transduction techniques and different sources also we have considered, like vibration energy, like we have solar energy, we have radio frequency as well as the thermal energy. But majority of the aspects we have discussed on the vibration energy. Then we have discussed the basic theoretical background with respect to the different transduction mechanisms like piezo, triboelectromagnetic, along with the hybridized mechanisms. And after that also we have discussed about the circuit implementation aspect. After creating the platform and background, then we have discussed about some of our past and ongoing research activities, and starting from the scratch how we have moved forward. And there are a lot of different other activities are also ongoing in these directions. So with this, we have shown some demonstrations of that ongoing research experiments as well, and finally we have given the ideas with respect to the cell power system concepts. So with this, I am concluding the session. If you have any doubts or any questions, please feel free to ask. So there are definitely, we should acknowledge the sponsoring agency. We have the CRB as well as our internal institute. Couple of students working in this, we have Durgapur, he is from basically IIT Kharagpur, he was associated there, and so these are the current students, and some B.Tech students, Akash is also there, and definitely we should acknowledge our associated center, Advanced Technology Development Center. And yeah, so with this, let us conclude the session. If you have any question, please let me know.
Still up to date, no store has been done of the vibration energy in a mechanical form.
Yeah, so that's what I said. So till now I am not aware of, but there may be something, but as of now I have not come across that. So something might
Then it will be very optimized utilization of the vibration energy, if it can be.
Yeah.
Because one time more car are passing heavy vibration, that output is not to be used 100%. But the rest balanced person, if I change it in the mechanical form, I can use atom when required.
Yeah, so electrically definitely you can do it and store it and use it for various batteries. But
not
in raw mechanical form, so right now I am
not
not
in
sure.
battery.
That can only be done in spring, nothing.
Yeah, so that's what I said. So
The spring,
simple
some kind of spring mechanism.
static energy is stored like that, but maybe some other.
One very crude method is change the deformation of the spring. Energy is deformation of the spring. Energy will be stored in the spring in the molecular form. And when you require that, when it will be required, the deformation of the spring will be again. There will be kinetic energy, potential energy in the spring.
Yeah, that is simply our, that earlier those watch, what we use basically. Any other classifications? So if not, so thank you all. So thanks to all the participants as well as the organizers.